Welcome everyone for the first lecture in the Deep Reinforcement Learning series. My name is Edward Young. I'm a final year PhD student here in the CBL, and I'm going to be delivering the sessions. Who's been to one of my lecture courses before? Hands up. Okay, lots of new people, which is great. Yeah, welcome. Okay, let's get started. We've got a lot to get through. What are we going to do today? Well, today is an introduction to reinforcement learning. So we're just going to be covering very basic concepts and ideas, just to make sure we all have a shared language with which to proceed for the rest of the course. So we're going to cover what makes RL different from other kinds of machine learning paradigms. We're going to cover the basic building blocks of RL. So what are like basic terms and definitions that you need to be familiar with. We're going to talk, a part of this is discussing environments, which is one of the sort of problem statement for RL. And we're going to discuss a taxonomy of different types of environments that your problem can fit in. We're going to give some examples, so you have like concrete versions of these things to use as illustrations in your own head. And then we're going to discuss returns and values, which again are sort of canonical items in reinforcement learning that we want to think about. And lastly, I'm going to give a brief overview of taxonomy of different RL algorithms and discuss what kinds of algorithms we're going to talk about in this course. Okay, so before we get into things, I'm just going to review what this course is going to cover. So this is today's lecture, Introduction to RL. Next week's lecture, we're going to cover dynamic programming, which is sort of the theoretical foundation of most modern RL algorithms. So it comes up for most modern RL algorithms, and it's important that you understand this idea very thoroughly, so we're going to dedicate a lecture to it. And at the end, we're going to discuss an algorithm called value iteration. This is the first one of our algorithms for this course. Then we're going to cover deep Q networks, which is historically speaking, the first real example of deep reinforcement learning. There are some precedents, but these aren't like particularly good. DQN is the first one where people realize like, you can use deep learning and reinforcement learning at the same time and do really, really, really well. Then we're going to discuss deep deterministic policy gradients, which is another algorithm, DDPG. Then we're going to cover advantage actor critic, and we're going to cover behavioral cloning, vanilla policy gradient, and advantage actor critic in this lecture. Proximal policy optimization. This is quite a fun lecture because PPO, proximal policy optimization, is one of the frontier algorithms that's used a lot. So if you're familiar with like modern AI systems like ChatGPT, this is trained through PPO, for example, or like previous iterations of it were. We have no idea how it's trained now. And then second to last, natural policy gradient methods. So natural policy gradient and trust region policy optimization. And then finally, we're going to cover some sort of more general aspects of RL and talk about using RL in practice and what we have to be aware of when we're actually deploying these algorithms. Okay. So a note about like course style. So this isn't an entirely practical course. Last year I ran a course with a more practical bent where we implemented some of the algorithms, but it's also not a theoretical course. So there will not be long derivations. There's in like the entire slide deck for all of the lectures, there's like one mathematical derivation. So we're not doing long mathematical derivations, but the aim is that you understand like the principles behind the algorithms. Not that you could like necessarily derive them for yourself, but that you understand like, why does this make sense? Like, why are we doing things this way? That you understand that these aren't like given from nowhere, that they come from somewhere, and that there's a justification, and you have this intuitive justification of why we do things a certain way and why those ways work. And yeah, I'm going to include pointers for like, where can you go to get the rigorous details if you want to? So typically this is just along the lines of like, what term should you Google to find the thing, the proof of the thing that I say? Great. Okay, so first section, what makes RL unique? So reinforcement learning is a paradigm within machine learning. It's a sort of problem statement. And to understand like what makes it different or interesting, I'm going to contrast it with supervised learning, which is another problem statement within machine learning that you may have already encountered. So let's look at the two of these. So the first axis we're going to compare these two on is data. Like, what does the data that I use to train my model look like in these two cases? So for supervised learning, you have a static data set that is given to you. So somebody comes to you and they say, I want you to fit a model that, given various biometric measurements of a person, predicts their risk of having a heart failure in the next 5 years, right? And then they give you, as input to like the problem, they give you a data set that contains like this collection of people who have all these measurements, and whether or not they did eventually have a heart failure in the 5 years following those measurements being taken, right? So someone gives you this static data set of, okay, here's an input, here's an output. I want you to build a model that sort of captures the relationship between inputs and outputs, so that if I give you fresh inputs where you don't know the output already, you can tell me what the output's going to be, right? This is how supervised learning works. And yeah, our task is learning this relationship between inputs and outputs, given the static data set that we're given. So how does data differ in reinforcement learning? So in reinforcement learning, data is sort of generated through a continual interaction with an environment. So in RL, we have a reinforcement learning agent that interacts continuously with some environment. And in that interaction, it elicits data from the environment itself, right? So by choosing to take certain actions, the agent learns things about the consequences of those actions in the environment, right? But then the agent has to, or in designing a good reinforcement learning algorithm, we need to be aware that the strategy we use for interacting with the environment is basically a strategy of data generation, right? It's a strategy of like, how am I going to elicit useful information from the environment? How am I going to query the environment so that I can get the kinds of data that's going to help me learn, right? And so unlike in supervised learning, we have control over the data that we get, right? We're not given a static data set, but instead we have to decide how we're going to elicit data so that we can learn effectively. So this immediately makes the problem way harder to solve, right? Because you have this entire other dimension that doesn't exist in supervised learning of working out how you're going to get the data that you need in order to learn the problem. Okay, so the second axis we're going to look at these on is evaluation. So how do we know that we're doing a good job in either of these cases? So for supervised learning, what doing a good job means is that if I give you a fresh set of inputs, then on each one of those inputs, you give me the correct label. So I give you a new collection of 10 people and their biometric measurements. Your model predicts like their likelihood of having a heart failure, and if you assign high likelihood to people who do go on to have a heart failure and low likelihood to those who don't, you've done a good job, right? This is what it means to do a good job in supervised learning, that you correctly predict the labels for a new set of people coming in. And an important part of this is that each individual each next person that you're seeing is basically independent from the others, right? So if I do a really good job of predicting the first person in my collection of 10 new people, I like say there's a 99% chance they have a heart failure and they do go on to have a heart failure, but I do terribly on all the others, it doesn't diminish the fact that I got the first one right. Each one of these tests is independent from all the others. I have 10 people, and each one I independently want to predict correctly what happens to that person, right? How is this different in reinforcement learning? So in reinforcement learning, when we're evaluating an agent, we don't just care about the agent's decision on a single time step. Instead, we care about the agent's total decision-making over the entire continuous interaction that the agent has with the environment, right? So instead of just asking, did the agent make a good decision on this time step, the question is, does the agent have a series of decisions which is good in aggregation? So each new problem that the agent faces of making a decision at each new time step depends on the previous decisions that it's made and will influence the decisions that it makes in the future. So we have this coupling over time steps that you don't have in supervised learning, where the problem we're trying to solve is fundamentally extended in time. A lot of this will make more sense when we discuss more about how the basic elements of reinforcement learning and how this loop of agent-environment interaction takes place. Okay, so let's start like building a vocabulary for reinforcement learning and understanding these basic terms. So the two basic things that we're going to deal with are environments and agents. Okay? And the environment begins in some state. So the environment starts off in some state. So this could be, for example, the starting state of a chessboard, right? Or you picture a chessboard, there's an initial state that it begins in, with the pieces laid out a certain way. And then the agent observes this state, so it gets to look at the current state that the environment's in, and decide, based upon that state, what action to take. So it takes some action. So maybe it moves like one of the center pawns two squares forward, right? This is the action that it takes. And in response to this action, the environment emits a reward that quantifies, gives some measure of how good the action was, and enters into some new state. So it transitions into some new state for the environment to be in. And then this interaction repeats over and over again. So this new state is then given to the agent again. The agent takes a new action, the environment emits a new reward and transitions into a new state. And we keep going on and on like this. So this process of passing back and forth states and actions, with the environment passing a state to the agent and the agent passing an action to the environment, this process repeats over and over again until you reach a terminal state. Typically, we denote the time at which this reaches capital T. And this entire interaction, this sequence of state, action, reward, on and on and on like this, is called a trajectory. This is another important terminology to know. So a trajectory is just this long sequence of states, actions, rewards, states, actions, rewards. And it describes the holistic interaction between the agent and the environment over many, many time steps. For many of the algorithms we're going to be considering, we care about small segments of this trajectory. And the segments we care about are called transitions. And for us, a transition is just going to mean a state, what action was taken in that state, what reward did I get from that action, and then what was the state that I ended up in after that. So S-A-R-S prime. So S prime denotes the next state. And I'm going to be using this notation a lot, right? So a transition is precisely this collection of four things. What state was I in? What action did I perform? What reward did I get? And what state did I end up in? And we can see that the trajectory can be sort of decomposed into like many of these transitions. So let's sort of like illustrate what's going on here, what this looks like. So I start with the environment, and the environment is going to pass to the agent an initial state, right? The agent takes in this state, and in response to this state, emits an action. So decides which action it wants to take. Then, in response to the action, the environment is going to first emit a reward, which gets sent to the agent, and transition into a new state. So this is what a transition looks like graphically. You have a state, then an action, then a reward, and then a next state. Okay? And then I can just loop this process over and over again. And if I loop this process over and over again, I get a trajectory, which is the complete interaction between an agent and environment from initial state to terminal state. Okay, great. So these interactions between agents and environments, you'll sometimes hear them called Markov decision processes. We're not going to use that terminology particularly often, but it's important to unpack it so that if you encounter it in the wild, you know what it means. So what's a Markov decision process? So it can be decomposed into Markov and decision process. Decision process refers to this continual interaction between the agent and the environment in a way where the agent is making decisions. The agent gets to choose which action to take, and for those decisions, it receives rewards. And this is what's meant by a decision process. Okay. What does the term Markov mean? So Markov refers to an independence of the future from the past. So let's like be a little more specific about that, in an MDP, a Markov decision process, the next state and the reward that I transition into, so this next state and the reward, these depend only on the state that I was in, so S, and the action I took. So you can think of, a good example of this is chess, right? So in chess, if I'm in a certain board, right, the board is set up a certain way, and I make a certain move. I move my queen, a certain way. The state that I end up in, the new board state, doesn't depend on how I got to that previous state, right? It's the same independent of how I got there. So the opening moves could be completely different, but if I eventually reach the same state and I do the same thing, I end up in the same place. And that's what the Markov part of Markov decision process means, that the future depends only on the present and not the past. So if I know the current state and the action I took in it, then I can tell you what the next state will be and what reward will be emitted, independent of what happened prior to the current state. Okay? So this is what we mean by a Markov decision process. So the reward and the next state depend only on the current state and the action taken in it. All right. Great. So now let's discuss some new terminology, policies. So the selection of actions by the agent is known as the agent's policy, right? So the agent has to take in states and emit actions, and this selection of which action to perform in which state is known as the agent's policy. Okay. And there's two types of policies. There's deterministic policies, which is whenever I see this state, I will perform this action. Right? This is a deterministic policy because it deterministically maps from states into actions. And you also have stochastic policies, which describe a distribution over actions in that state. So I say, when I'm in this state, there's a 50% chance of doing this and a 50% chance of doing that, for example. And when I'm in this state, there's a 75% chance of doing the first action and a 25% chance of doing the second, right? So stochastic policy takes in states, and for each one of those states returns probabilities of performing each different action that could be performed in that state. Okay? And this is contrasted to a deterministic policy, where you just take in a state and you say what action I'm going to do in that state. And it's always the same action in the same state. All right? Great. I'm going to pause briefly. Does anyone have any questions at this point? Yes, we can keep going. Cool. Great. Let's keep going. So the next discussion is types of environments. So we just covered types of policies, and we're going to see that environments look very similar. So first distinction is between continuous and discrete state spaces. So the state space is just the collection of all of the states for the environment, right? So you could think of this for chess. The state space is all possible chess boards, right? And this state space can be either continuous or discrete. So a continuous state space is a state space that's described by some continuous set of parameters, and there's infinitely many of these. So an example of this of a continuous state would be if I have a ball, the position of the ball in space is a continuous state because I can continually move it about in space and get new states wherever I go to. Chess, on the other hand, is an example of a discrete state space because there are only finitely many boards. There are a ridiculously large number of boards, but there's only finitely many, right? So chess has a discrete state space. So discrete means you have a finite collection of states, and continuous means you have infinitely many states, and you can usually describe these in terms of a collection of variables. So for example, the position and velocity of a point, for example. We're going to see some examples of these, so if it's not quite clicking yet, don't worry. We're about to get to some concrete examples that we can go through. And just as our states can be continuous or discrete, our action space can also be continuous or discrete. So the action space is just a set of all possible actions that can be performed in each state in the environment. So for chess, it's all valid chess moves that I could perform, right? And again, this can either be continuous or discrete, meaning exactly the same thing, right? So this distinction between continuous and discrete matters a lot more for action spaces than it does for state spaces. So in general, pretty much all of the algorithms that we're going to consider work basically exactly as well if you have a continuous state space or a discrete state space. But some of the actions you can only use on one of the two, right? So the distinction between continuous and discrete action spaces matters in terms of choosing which algorithm to use, because only some algorithms can be used on continuous state spaces and only some can be used on discrete. And that's one of the things we'll cover for each algorithm. What action spaces is it valid for? And then just as we had deterministic and stochastic policies, we also have deterministic and stochastic environments. So this means basically the same thing. In a deterministic environment, if you're in the same state and you perform the same action, then you always get the same reward and the same next state, right? Whereas for a stochastic environment is described by a distribution over what reward you get and what state you enter into, given that you're in a certain state and you perform a certain action. So there's some randomness there, there's some chance. So the way we describe environments is using their dynamics function. So the dynamics function is a specification of the probability of getting a specific reward and transitioning into a certain next state, conditional that I take a certain action in a certain state. And we denote it like this. So this is the probability of ending up in a certain state, so ending up in a certain next state, and getting a certain reward, given that I start in a certain state and I perform a certain action. Right? So given that I'm in S and I do action A, this gives me the probability of ending up in S prime and getting a reward R. In deterministic environments, this has support only for one next state reward pair. So it's a degenerate probability distribution. It has support only on one place. You deterministically transition like this. Okay, great. So maybe these ideas are not entirely clear yet. Hopefully they will become clear once you have some concrete examples to illustrate these differences. Okay, so here's our first example. This environment is called maze. And in maze, you start off in the top left-hand corner, and you have to navigate your way to the cheese in the bottom right-hand corner, right? Yeah, very straightforward. Okay, so you have a grid of squares. Some of them are impassable. These are walls. And the state is just what position you're currently in, right? So the state of the environment is which square do you currently occupy, right? And your actions are up, down, left, and right. And sometimes these don't do anything. So if I'm here, for example, and I choose to go left, then nothing's going to happen. I'm going to stay where I am. If I'm here and I choose to go right, I'm going to transition into this state here. Okay. And the rewards are sparse. And by this we mean that basically every transition doesn't give you a reward. The only transition where you do get a reward is when you're here or here and you move onto the cheese. So you get a reward of +1 when you move onto the cheese. Okay, so first question, is this state space continuous or discrete? So hands up for continuous, hands up for discrete. Perfect, great, we understand the assignment. Is the action space continuous or discrete? Continuous? Discrete? Fantastic. And is it a stochastic or deterministic environment? Stochastic? Deterministic? Yeah, it's a deterministic environment because if I'm here and I go down, then I'm always going to end up here. There's no randomness involved. Okay, bit harder. Cart pole. Cart pole is a classic because if your algorithm can't solve cart pole, it definitely doesn't work. So you know that you've implemented it wrong. So cart pole, you start with a pole that's just off the vertical, and then the environment is described by the position of the cart along here and the velocity that it's traveling along with the angle that this pole makes with the vertical and the angular momentum that it has. So you have these like 4 variables that collectively describe the state. Okay? The 2 actions that you can perform are move left or move right, or more precisely, exert a force of 1 Newton left or a force of 1 Newton right, which isn't quite the same as moving left or right because this just changes your acceleration. It doesn't change your velocity, and so you have to like be very careful to exert the right amount of force so you don't over-accelerate. What does it mean to over-accelerate? Well, what you're trying to do is keep this pole vertical. So you get a reward of +1 on every time step that the pole is within 24 degrees of the vertical. So you can imagine like 24-degree lines coming out here and here, and for every time step that you're between those lines, you get a reward of +1. Once you're not, the episode terminates and you're over. Right. So this reward signal is extremely non-sparse in that you have rewards everywhere, except for when you go out. There's only one time step where you don't have a reward. Okay, is the state space continuous? Discrete? It's continuous, yeah, because it's described by this collection of 4 variables: position, momentum, angular momentum, and velocity, right? So there's 4 collection of variables that I can vary continuously. This cart can move anywhere along this track. Action space continuous? Discrete? Yep, because there's 2 actions you can perform, left or right. So it's a discrete action space. And is it stochastic or deterministic? Stochastic? Deterministic? Yeah. So there is some randomness, but not in the dynamics. The randomness is in your initial state. So you get randomly initialized to like some number of degrees off the vertical. So there is some randomness, but not in the dynamics. It's a deterministic environment. Brilliant stuff. Ant. Look at it go. Horrific. So the states in Ant are the positions, velocities, angles, and angular velocities of all of the different body parts. So all of these different hinges coming off this freaky little body. And this is what describes the state. The actions you can perform are for each one of these different joints. You can exert some force on it. You can exert a torque between -1 and +1 Newton meters. So you can exert some torque between these 2 values for each one of these different joints. And the rewards, it's a very complicated reward function, so I'm not going to list them out, but you get rewards if you move forward, if you stay upright, if your body's not touching the floor, and if you get like penalized, so negative reward, which is a penalty, if you exert large amounts of torque on the different joints. So you get penalized for having very strong torque on the joints. Okay, is the state space continuous? Discrete? Yeah, continuous, right? All of these different variables, the positions and the momentum, right? Continuous state space. Is the action space continuous? Discrete? Yeah, it's continuous. Why? Because you can exert any force between -1 and +1 Newton meters. So there's a continuum of different forces you can exert. It differs from cart pole. In the cart pole, it's 1 Newton one way or 1 Newton meter, 1 Newton the other way. Here, you have a variable torque that you can apply. And is the environment stochastic or deterministic? Yeah, it's a deterministic environment. It's built on top of a physics engine called Mujoko, and the same actions always lead to the same next state. Fantastic. Okay, Blackjack is one of the Atari games. There's a game suite called Atari. And your state is just what cards do you currently hold, and what cards does the dealer currently hold. And actions are stick or hit. You know how to play Blackjack, probably. I'm not going to go through the rules of Blackjack here. You get a +1 if you win, -1 for losing, 0 if you draw. So again, sparse in the sense that you don't get much of a reward signal except at the ends of episodes. By the way, was the Mujiko environment, so was Ant sparse or non-sparse? Sparse? Non-sparse? Yeah, non-sparse, because you get like lots of feedback. Like, are you currently moving forward? Is your body off the ground? Like, have you exerted lots of force? You get lots and lots of feedback from the environment about whether you're doing a good job. So it's a very non-sparse signal. Okay, continuous, discrete, yeah, because there's like finitely many different card hands that you could hold and cards that could be in the deck. Action space, continuous, discrete, fantastic, yep, because there's only two things you can do. And stochastic or deterministic. So it's a stochastic environment because there's randomness about which cards you're dealt. Yeah, okay, fantastic. Oh, okay, yeah, and then all the other Atari games. So the Donkey Kong, Tetris, Pac-Man, Breakout. Actions are which buttons do you want to press on the console. And the states are typically collections of like 4 frames consecutively. It's usually 4 frames. So like this is necessary because if you're playing something like Breakout and you can only see 1 frame at a time, like if the ball is here, then I don't know whether it's coming towards me or away from me, and this does a lot to affect like which action I should take. But if I have 4 consecutive frames, I can see like, the ball's moving like here, and then here, and then here. It's going away from me, right? So I stack 4 frames consecutively, and this is like enough to tell me what's happening in the environment. And the rewards like vary massively between games, right? It's typically like in Tetris, it's this number. Breakout, it's this number. Donkey Kong is this number, right? State space, continuous, discrete. It's actually continuous. And the reason is because it's specified by the RGB values for every single different pixel on this frame. Now, technically speaking, this is actually discrete because there are finitely many of them. But like, it's much more helpful to think of it as like a continuous value of like what the luminance of each of these different channels is. And the reason for that is because, again, these have the structure of a continuous state space in that there is like a continuity between them. If I take this state and I put like a red pixel here, it's like essentially exactly the same state, right? And so there's continuity between states that are like close together in RGB value, and so it makes sense to think of it like a continuous state space. But discrete is like a perfectly valid answer. There are only like finitely many screens you could see. Action space, continuous, discrete. Yeah, it's discrete. There's finitely many buttons. Which buttons I press, that's my actions. So finitely many actions I could take. Finally, stochastic or deterministic. Depends on the game. I think that most of the games in the Atari suite end up being deterministic, but I'm not actually sure about this. Yeah, depends on the game. Fantastic. Any questions at this point?
I just wanted to compare the 2 ways that you deliver dynamics of the environment in the Atari game versus in like the cardboard game. In one case, in a cardboard game, you provide information about the angle of momentum and all the other dynamics of the agent. But in the Atari game, you just give the last 4 frames.
Yeah.
I'm just wondering how much does that actually limit the extras of learn these dynamics? Does that mean like a systematic study?
So
from snapshots as opposed to providing information about the
I bet people have looked at this, but I don't know about the general case. Yeah.
So the most successful algorithms for the Atari stuff, or some of the most successful ones, do have separate like encoders or decoders which kind of extract the latent state vector from the image.
Yeah. Cool. Any other questions? Yeah.
Is there a special consideration when the agent, the action of the agent actually change the environment? It's like a financial market. The agent push for a bid for a thing, then request kind of up or down.
So this is like the default case in reinforcement learning, that the environment is responding to the agent's actions, right? And this is what makes it a reinforcement learning problem. So if it were the case that the environment would transition into a new state regardless of which action the agent took, then this is no longer an RL problem, because the actions I take have no effect on what happens in the environment. So the default setting in RL is that what action I take changes how the environment evolves in the future. Great. So we've talked a lot about like environments and policies and all this. We haven't actually talked like what is the reinforcement learning problem? What are we like trying to do? What's the point of the exercise? So the goal of RL is to maximize the return of trajectories. So we know what a trajectory is. It's this long sequence of state, action, reward, state, action, reward. It's this long sequence of interactions between the agent and the environment. And we want to generate trajectories. Our aim is to have a policy that generates trajectories which have as high a return as possible. So this just kicks things up one level. What's the return? So the return of a trajectory is the sum of rewards across that trajectory. So the return of a trajectory is just the sum of the rewards. So we immediately see how reinforcement learning ends up having this coupling between each different segment of my interactions in a way that supervised learning doesn't, right? This thing I talked about at the start. In that there's cases where I might want to, I might have an action available to me that generates a very high return, a very high reward immediately. There's got like plus 10 reward attached to it. But it transitions me into a state where it's a very bad state to be in. And I can't get any more rewards from that state at all, right? Whereas there might be another action I could take that doesn't generate any immediately reward, but does put me in an excellent position later on, right? And this in very human terms, this is the problem of delayed gratification, right? Like sometimes there are things that we can do that don't bring us immediate benefit, but do bring us benefit later on. And we want our agent to learn how to do those things, right? Like a PhD. So the return is just this sum of rewards over the entire trajectory. And we want to maximize this quantity. We're also going to use, this is the return at time 0. This is the thing that we care about maximizing, a return at time 0. But we're also going to define, because it's going to come up a lot, the return at time t. So this is all of the future rewards at time t. So I'm in a particular state, I perform a certain action. What is the sequence of rewards I get following that? Okay? So the return at time t is just all of the rewards following time t. So rt plus 1, t plus 2, all the way up to r capital T, the final reward that I get on the last time step. Fantastic. Yeah. The next concept to introduce is that of discounting. So discounting is when we reduce the value of rewards that happen further away from us in time. And the way we do this is that for every time step we go forward, for every new time step forward these rewards are detached from us, we're going to multiply them by what's called a discount factor, gamma. Gamma is typically, it's always less than 1, which means I'm down-weighting rewards that happen further away in time. And typically it's like pretty close to 1. Like a normal number for gamma to be is 0.99. This is a very normal number to see. And it just means that if I could choose between getting plus 1 now or plus 1 in one time step, then I would, the value of plus 1 in one time step is just gamma or 0.99. So I'm discounting it by a factor of gamma. So the undiscounted return is this thing that we met last time. It's this sum of rewards, right? So the sum of all of these rewards in the future. Whereas the discounted return looks like this. So I have my immediate reward plus the reward after that multiplied by 1 discount factor. Then the reward after that multiplied by 2 discount factors. Then the reward after that multiplied by 3 discount factors, and on and on and on up until the final time step. Okay? So every new time step I go forward, I pick up 1 new discount factor. And now we can return to the question of if I'm just in a maze and I just want my agent to complete the maze, I'm always going to get a plus 1 reward for completing it, and there's no other way for the episode to end. Why would the agent ever learn to complete it quickly? Well, if I put a discount factor in my equations and I try to maximize the discounted return, then essentially it's going to get a plus 1 reward times by the discount factor to the power of how many time steps it took, right? So it takes 100 time steps, then the return that it's going to get is gamma to the 100. If it takes 50 time steps, it's gamma to the 50. So it can get more discounted return by by using fewer time steps. Okay. So this is one reason we use discounting, to encourage the algorithm to get rewards sooner. There's actually other reasons we use it, and we're going to talk like a lot more about this next week. Yeah, discounting is like major topic of next week. Okay, so we now know what the basic problem statement of RL is. And now we're going to talk about value functions. So value functions are another like fundamental object that we're going to be using throughout many, I think literally all but one or two of the algorithms that we're going to discuss use value functions in some place. So these are like another fundamental building block for everything that's to come. So a value quantifies essentially how much return or how much total reward, so return is just total cumulative future reward, can I expect to get from taking a certain action or from being in a certain state. All right? So to make this precise, they are expected discounted returns conditional on something. Right? So return, sum of future rewards, discounted, rewards that are further away get down weighted, and expected means not just what happened, but what will happen in expectation. Averaged over all possible outcomes, what happens? So let's like write down the formulas for these. So my action value function, a bit complicated. Let's unpack it. So this is the action value function. Action value function is noted by a Q. No one knows why. And it's the value of being in state S and taking action A. All right. The pi here denotes that it's the value with respect to a certain policy. So it's the value that a certain policy has of being in a certain state and taking a certain action. And so expected discounted returns, that's like work backwards. This thing here, this is just the sum of all future rewards, which is the return, with a discount for each time step I go forward in the future. So this is the discounted return. And I'm conditioning on being in a certain state and taking a certain action, and then I'm asking, what do I expect this to be? So what is the expectation of this, given that I condition on this? Right? So given that I condition on being in a certain state and taking a certain action. Okay? A state value function defined extremely similarly, except now I'm conditioning only on being in a certain state. Right? So first thing, why is there a dependence on pi here? Well, the future rewards that I expect to get depend on what policy I'm pursuing. Right? If I'm in a certain state and I perform a certain action, then this might be really good for one policy and really bad for another. Right? Whereas, so there's a dependence on which policy I'm pursuing. Okay. Does anyone have questions about these? There's like quite a lot going on here. So if people have like uncertainties, then we can discuss them now. But we will be discussing these like a lot more next week. I just want to sort of introduce them now, so it's not like a complete shock next week. Yeah. So it's not that I'm averaging over policies. So it's not an expectation where I'm averaging over different policies. It's instead I'm averaging futures over a single policy. So I say if I get my policy and I put it back in this state 100 times, and I run it from that state 100 times, and I get the discounted return that it generates on each one of those 100 occasions, and I average them, what's that number going to be? Did you have a follow-up?
Oh, yeah, sorry. I meant they vary the policy to find the best action.
Yeah, so this is precisely what we're going to do. Right? The aim is to like keep increasing or keep changing pi so that this keeps getting higher and higher. Right? This is like fundamentally how we're going to solve the problem. Great. There's a question at the back. So if it's deterministic, then this is this collapses into just like the app. There's a single trajectory that's generated, right? So for a deterministic policy in a deterministic environment, there is a single sequence of rewards that you get from being in a certain state, and this is just whatever that sequence of rewards is. Yeah. Yeah, precisely. So there's a t in this, but the t doesn't matter. And the reason it doesn't matter is this Markovian property of the environment. That if I'm in a certain state and I perform a certain action, the value of that is the same independent of how I got there or when I got there. So this t doesn't actually matter. You can replace these t's with zeros if it helps, and it's the same definition. Okay, we've got 10 minutes left because I started slightly late. I'm just going to briefly cover types of RL algorithms. This is going to serve as a taxonomy of what we're going to cover in the course. So the first distinction is online versus offline. So in online RL, this describes the setup that I gave at the start, where I continually interact with an environment, I use that interaction to gather data, and I use that data to train my model, right? So I'm continually gathering information about the environment's dynamics. And then I'm in control of what data I gather, right? In offline RL, I'm just given a set of interactions to learn from. So I start with, someone gives me a big batch of previously in the past, this action caused this reward and this next state. I have a big batch of these, and I try to learn from this static fixed set. And this is generally way harder because you don't have control over what data you get. So this is a much harder problem to solve. And I think one algorithm in the course is going to address this, and all of the others are going to be online because online is much easier as a problem. Great. The next one is model-based versus model-free. So this distinction comes from whether or not I am given or I use a model of the environment's dynamics. So all of the deep reinforcement learning algorithms are going to use neural networks as models, but this is distinct from modeling the dynamics. So in RL, when we talk about something being model-based, we mean that it models or uses a model of the dynamics of the environment, right? So I try to learn this function. And yeah, sometimes there's also model-based algorithms that just, you give them environment dynamics. You say, here are your environment dynamics, do what you can using these. But typically we're trying to learn a model from data. So we're trying to learn this function here in a model-based algorithm. And a model-free algorithm learns directly from interactions without needing to learn the dynamics themselves. So you just run it against the environment, and it learns from that. It doesn't need to learn a dynamics function. You don't need to go via learning dynamics. So you just sample trajectories from the environment, and you use these samples to learn. And again, yeah, our focus. So we're going to be doing online reinforcement learning most of the time. The offline case is much harder. And we're going to be doing model-free algorithms. The reason for using model-free algorithms, or for focusing on that, is that these sort of form the building blocks that a lot of model-based algorithms end up using. Also, they're sort of the sort of canon is these model-free algorithms. Great. Okay. On policy versus off policy. So on policy means that the data that I use to learn things about either how I need to change my policy, or what values different actions have, this data has to be generated by the current policy that I'm trying to improve, right? So I have my current policy, I want to improve this one, and I can only use data that has been generated by that policy. This is what makes something on policy. Okay. This is in contrast to off policy, where the data that I can use for improving my current policy or making my action value function better can come from anywhere. So I can use it. I can use experience generated from other policies. And typically, how this manifests for us is going to be that the other policies generating data are old policies. So I have my first policy, I use it to generate data, and then I have and then I get a second policy, and I can reuse that first batch of data again for learning for the second policy. This is what makes something off policy, is that I can reuse old data. Concretely, this manifests itself as the use of a memory replay buffer. So a hallmark of this, something that goes along with off policy methods, is the use of something called a memory replay buffer. And the way a memory replay buffer works is that you load experiences into it, and then you recall them at some later point in time. And if you can learn from any experience, if you're off policy and you can learn from any experience, then you can just like load everything that you've experienced into this buffer and recall it whenever you want to learn, right? And this is in contrast to on policy, where you typically don't have a memory replay buffer because you can't use experience that was gathered by a policy way back, 10 iterations ago. Because you can reuse experience, off-policy methods tend to be more sample efficient, which means that they tend to achieve a higher score, a higher total return after fewer interactions with the environment, because you can reuse old experience. Whereas on-policy algorithms tend to be more stable, often because the data that they're learning from is data that is directly relevant to the current policy that's being learned. So you sort of have a direct correspondence between what you're trying to learn and the information that you have to learn from. We're going to start with off-policy methods and move on to on-policy methods later in the course. Like first 4 lectures are on-policy, I think, or off-policy, I think, and then later ones we discuss on-policy methods. Finally, last one, action value versus policy gradient. So an action value method learns a value function for actions. So I have different actions available for me, and I learn the value that these different actions have, and I use that to choose which action to take. And typically this amounts to like trying to choose the action that maximizes this action value function. Yeah.
How is this different from learning Q?
It is learning Q. Yeah. So action value methods are methods which try to learn this Q function, Q of state and action path, right? In contrast, we have policy gradient methods, which directly learn some policy for interacting with the environment. So in this case, your policy is like a tacit policy that is defined by an action value function, whereas here you have an explicit policy, and you just try to update this policy and make it better over time. And methods that use both the value function and the policy are typically called actor-critic methods. So the policy is an actor, it behaves in the environment, it takes actions, and the value function is a critic, which basically evaluates the actions that the policy has taken and tells it whether they were good actions or bad actions. And this is used to adjust the weight that the policy assigns to those actions. So the value function is used to critique the actor. Final diagram. So we have methods that learn a value function, right, in this circle here. And then we have methods that learn a policy. These are policy gradient methods. Okay, so here we have action value methods. So these are methods that just learn an action value function, but do not learn a policy. Here we have pure policy gradient methods, where I don't learn an action value function, I just learn a policy. And in the middle, we have actor-critic methods, where I'm both learning a policy and I'm learning a value function. Okay, fantastic. Thank you all for listening.